So what do you do if you want to find the average velocity of an object if all we know is the position function? Well, this is Climb Time, and in this video, we're going to find out how to find the average velocity when given a position function and a time interval. To start with, we have the position function 64 minus 6 times the quantity t minus 1 squared. This position function looks something like this, as you can see on the graph there. And it basically is modeling an object being thrown into the air. And this is before it hits its peak and starts coming back down again. And you can see that there is a time of 0.4 seconds and a time of 0.8 seconds. And the corresponding y values is corresponding position. So the s represents a height with respect to the ground. And so the function is this right here, as we can see. And this is the time interval we're looking at from 0.4 to 0.8 seconds. What is the average velocity from 0.4 to 0.8? And we're going to take a look and see how these averaged velocities compare around the time 0.8 seconds. But we're starting with 0.4 to 0.8. So what we need to do is we need to know the average value function. And the average velocity is found by taking the position function evaluated at the later point, that b, minus the position function evaluated at the earlier point, we'll call that a, and divide that by b minus a. Okay, that is the general function right there for the average velocity. So in this specific case, we are going to plug in, 0.8 seconds, because that is the one that's a little bit farther along. And then the one that is closer to the origin, 0.4 seconds, and divide that by 0.8 minus 0.4. And so that is the general function, and this is how you find the average velocity. And what the average velocity is it is basically the slope of the line that connects these two points. So we're looking at the slope of that line, and because the position is in feet, and I'll put feet in parentheses here, and the time is in seconds, the sloped line is rise over run, so it's in feet per second. So that is a unit of velocity or speed. So now what we got to do is we got to actually figure out what s of 0.8 is and s of 0.4. So we have to plug those into the functions to find out what we get. So s of 0.8 is going to equal, and now we have to plug into that function right there. So you have 64 minus 16 times 0.8 minus 1 squared, and that's s of 0.8. And if we simplify that, 0.8 minus 1 is 0.2, and then square that, that's 0.04. Anyhow, we can simplify the math, and it comes out to be 63.36. Let's look at my notes there. So 63.36 after simplifying that math there. Now, s of 0.4, it's the same idea. We're going to plug in 0.4 into the same function. So get 0.4 minus 1 squared. And after we simplify the math on that, 0.4 minus 1 squared, multiplied by 16, and we come out with 58.24. So what these numbers mean is 63.36 is the height in feet at 0.8 seconds. So that means over here, we could draw a little dashed line. We could say, okay, we know that at 0.4 seconds, it was at 58.24. And then at 0.8 seconds, it was a little higher at 63 and some change. So I'll just say approximately 63. So that's the height at those two spots. So we have 56.36 and 58.24. And our average velocity is the slope of the line, which is the change in the y values, which is the difference in these two. So we have 63.36 minus 58.24, and then divide that by 0.8 minus 0.4, which is 0.4. Okay, if we do the math on that, we will come out with, and I will take a look at my notes here, 12.8 feet per second. So the average velocity comes out to be 12.8 feet per second. Okay, and so that's how you find the average velocity when given the position curve. So from 0.4 to 0.8, it is 12.8 feet per second. All right, so that would be a lot of work to do all of these by hand. So we're not going to do them all by hand. We're instead going to use a graphing calculator to help us with the function values there, because that's really the most tedious work right there is the function values. And we're going to see if we can come up with all the different average velocities over these different time intervals. Let's first talk about what we would expect. So 12.8 is the slope of the line, so it's going to have a certain steepness to it. But if I get closer to the 0.8, I'm back at 0.7, you can see the line starting to curve like this. And so because the line's starting to curve, we would expect the slope of the line to get more flat, more horizontal. And so we'd expect the slope of this one right here to be a smaller number, closer to 0. So let's see what happens. We are going to use the same formula. It's going to be S of B minus S of A all over B minus A. But for this one, we're actually going to look at 0.8 and 0.7. So S of 0.8 minus S of 0.7. And all over 0.8 minus 0.7. And now I'm going to let my graphing calculator, and if you don't know how to do that, I've made a video how to use a TI-84 to find function values. So check out that video if you're not sure how to find function values using graphing calculator. Specifically, TI-84 is the one I gave a demo of. All right, so the values come out to be 63.36. So this is 63.36. And then this one comes out to be 62.56. 62.56. And that's all over. 0.8 minus 0.7 is 0.1. Let me box this, by the way, because that was our important result. And so if you do the math on that, take that minus that and divide it by 0.1, you're going to come out with a solid 8 feet per second. So as we expected, that number is closer to 0. The line is going to be, let's just do 1 here. The line is going to be more flat because as we get closer to 0.8, these lines are going to get more and more flat as the interval is getting closer to 0.8. So let's write that in. That's 8 feet per second. Okay, and notice the next one here, and then we can keep going, do the same process. The next one is 0.79 to 0.8. And so we would expect, again, for it to get flatter, again, so the number to get closer to 0. And so that number is going to come out to be 6.56, following that same methodology there. And see, you can tell we're getting closer and closer to 0.8, 0.799 to 0.8. So we're getting very, very, very close to 0.8. And we're trying to figure out what the velocity is basically at 0.8 seconds. And so as we make our intervals smaller, 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 we're finding an average velocity that's closer and closer and closer to 0.8. So we're basically trying to hone in on the instant velocity, what we call instant velocity at 0.8 seconds. So what we'd expect, again, since it's getting a little flatter, is a number smaller than 6 or 6.56. And sure enough, the next one is 6.416. 6.416 feet per second. So exactly what we'd expect there. So this is coming from the left. So all of this is coming from the left. So let's write that in here. So this is coming from the left. All right, so coming from the left, that's what we got. Now let's take a look and see what happens when we're coming from the right. So if we're coming from the right, what we'd expect is numbers maybe getting, oops, I smeared that a little bit. I don't like that. Let's put that back in there. What we'd expect is numbers that are, again, still a little flatter because we haven't reached the peak of this curve. So I still expect the slope to get a little flatter. And so a number smaller than 6.416. And sure enough, we do. We have a number 6.384 feet per second. And then that's just going from 0.8 to 0.801. So 1,000th of a second after 0.8. And then this is 100th of a second after 0.8. So this is a little farther out than that one. This one comes out to be 6.24 seconds. Or sorry, 6.24 feet per second. And now we're a whole tenth away from 0.8. That comes out to be 4.8. You can tell now because we are moving farther and farther away from 0.8, it's diverging farther and farther from this sort of central spot in here. And then we'd expect this number to be even smaller yet and smaller away from this sort of like 6 range that we had over here when we were very, very close to 0.8. Here we're 100th off, here we're 1,000th off, here we're 1,000th off, here we're 100th off. And you can see we're getting very close to the same number as we get closer and closer to 0.8. But as we get farther and farther away from 0.8, the number gets farther and farther off. And in fact, this comes out to be 0 feet per second. Okay, and so you can see what's happening here is that we are getting values that are closer and closer and closer to a single value. And what that value is, hard to say, maybe 6.4, something around that range. Maybe I'll put in 6.4 and a question mark because it's hard to know exactly what it is, but we know it's somewhere. It's somewhere between 6.416 and 6.384. And so we would call that at t equals 0.8 seconds, we call that an instant velocity or instantaneous velocity. And so the average velocities are always between 2 points. And so between 2 points, we have these different average velocities. And again, as we get closer and closer and closer to 0.8, the number starts to converge on a single number. And as we get, again, we're still closer to 0.8 from the right. And so maybe I'll put that in over here. So from the right. So from the left and from the right, we're getting closer and closer and closer to the same number, converging on the same number. And that same number is what we call an instantaneous velocity. But this is the process and how you do it. And this is the formula defining an average velocity with a position function. It is S of B minus S of A over B minus A. It is rise over run, changing your Y values over changing your X values. And so the average velocity is the slope of the line that connects 2 points on the position function.